Hi, the purpose of this video is to go through the equation for exponential decay. In a previous video we went through exponential growth. This will be a very similar process. The equation is relatively the same. There's just one change, and that's your base being a number smaller than 1 instead of bigger than 1. Okay, so all of these same constants and variables follow with before. So A is your new amount. Sometimes they talk about that as your output or your Y. P is your original amount. They call that the principal in a lot of cases. R is your rate of change. They usually present that in a percentage and you convert it to a decimal. T is time in years for now, unless otherwise stated. And then this is the new part. You have your 1 minus the rate instead of 1 plus the rate. That gives us our decay factor. So we're starting off large, decreasing rapidly, and then flattening out like a decay graph. Okay. A quick reminder that some of these letters are sometimes used differently, or they're replaced with other things in different textbooks, but the structure is pretty consistent. These words are what we can look for if we're identifying a decay problem. As we start to mix up problems together, you want to look for these to as an indication that it's a decay graph. So obviously decay itself, the trickiest one is probably the word depreciate, and then decreasing is also important there. Okay, so similar in structure to the problems from before, but you're just looking for something that starts off at a higher value and then will decrease in value as it goes, okay, or quantity. So a car is a good example of that. So cars start selling at $22,300 is known to depreciate at a rate of 11% per year. Start off by writing that equation, and then they are having you here replace the A with a V for your output, okay, at the end, and T remains your years. So we look for our initial amount, that's 22,300. Our rate is 11%, so you convert that to a decimal, 0.11, and your decay factor is 1 minus that rate, so 0.89. Okay, and make sure you write it with that 0.89 in the equation for a few different reasons. It's easier to type, and when you look at it quickly, we can see that this number is smaller than 1 without all that extra stuff involved. Okay, so obviously sometimes they have you write the equation, then they have you plug in a certain amount of years to see what values are or quantities are after a certain amount of time. So in this case, for part B, they want you to look at the value of this car after 7 years. So remember, it started off at $22,300. After 7 years, it's down to about $9,869.59. All you have to do once you have your equation is plug that whole thing in one step. Most calculators have this caret button indicating an exponent, so you could do that. Some calculators are a little annoying. They have an A-B button where you have to do things in steps, but most modern calculators can allow you to type it all in this way. Okay, if you do only have your phone, I recommend downloading the Desmos scientific calculator. It's a little nicer than the calculator they provide for you on the phone with that kind of stuff. Okay, and usually there's some kind of follow-up question about the properties of the graph. So part C here talks about, converting the rate to 9% rather than 11%. How would the graphs differ? Well, logically, you would think something's decreasing at 11% originally, and then it changes to 9%. That rate of change is going to slow down. So that same thing's going to happen in your graph. So your rate of decay for the original was 0.89. The rate of decay for that 9% one was 0.91. So if you were to plot both of those on the same coordinate grid, the original one would decay at a faster rate, 11%, than the new one at 9%, and so they both kind of flatten out around the same area, but the initial decay over a period of time will be much faster for the 11% decay. Okay, so that's pretty much it. There is a tricky scenario sometimes students have trouble with, so I'll move down to that problem real quick if you have this handout. Number 2 here, or if you're just watching, just follow along. So the value of a laser printer after T years is V equals 371, and then the base of 0.82 to the T power. Part A asks about the cost of the printer when it's new. Well, that's your initial value. That's the number in the front. That's pretty straightforward, but a lot of students have trouble with the annual rate. Now remember, in the original problem, it was 1 minus the rate to get this number 0.82. So this number 0.82 plus your rate will give you 1. Okay, if you work backwards from there. Okay, so all you have to do is do 1 minus the number presented there to get your rate, so we can find out that our rate of decay is 18%. Okay, so lots of little variations of that, but that's the meat and potatoes of what you need to know for this concept. Hopefully it was informative in this video. Thanks for watching and have a good day.